Let's talk about 30, 60, 90 triangles and 45, 45, 90 triangles. These are right triangles that have special properties that allow us to calculate exact side lengths more easily. To solve these triangles, we're going to set up a proportion. And the proportion for a 45, 45, 90 triangle is 1, 1, square root of 2. The 1s are referring to the legs, and the square root of 2 is referring to the hypotenuse. It makes sense to have two legs that are the same measurement because we have two angles that are the same measure. Since these two angles are both 45 degrees, this must be an isosceles triangle, which means these two sides must be the same. So that's why the legs are in a 1-to-1 ratio. But where did this square root of 2 come from? Well, you could actually figure it out using the Pythagorean theorem. You could say that 1 squared plus 1 squared equals the hypotenuse squared. And 1 squared plus 1 squared is 2. So if I were to solve 2 equals hypotenuse squared, I would have to square root 2. So that's where I get this square root of 2 from. So to calculate a side length in a 45, 45, 90 triangle, you can just take the numbers from your diagram and place them into your proportion and solve. And you could do something similar for a 30, 60, 90 triangle. The ratio of the side lengths in a 30, 60, 90 triangle is 1, square root of 3, and 2. 1 is referring to the short leg. The short leg is the one that's across from the smaller angle. Square root of 3 is referring to the long leg. The long leg is the one that's across from the bigger angle. And 2 is referring to the hypotenuse, which of course is the side across from the right angle. So just like a 45, 45, 90 triangle, you can solve a 30, 60, 90 triangle by taking the numbers from your diagram and putting them into this proportion. So let's give it a try. The first thing you need to do each time is determine which kind of special triangle you're looking at. In this case, we have a 45, 45, 90 triangle, so the ratio that I'll use to solve is 1, 1, square root of 2. Each of the 1s are referring to the legs. One of my legs is 3, the other is x. And square root of 2 matches to the hypotenuse, which for this diagram is y. Now that I've set up the complete proportion, I need to pick two ratios from it to solve for each of my variables. So for example, I could use the first two ratios here, cross multiply and solve, and figure out that x equals 3. Realistically though, we really didn't need to show that work because since this is a 45, 45, 90 triangle, I know that the legs must be congruent to each other. So since one of the legs was 3 kilometers, x must be 3 kilometers as well. But we do have to use a proportion and cross multiply to calculate y. So I'll take this ratio that has y and this ratio that's complete that I know both the top and the bottom number. So I'll write that 1/3 equals the square root of 2 over y. Then I can cross multiply and solve, and I get an answer of y equals 3 times the square root of 2. Next up we have another 45, 45, 90 triangle, but this time I don't know either of the legs. So let's go ahead and set up our proportion, 1, 1, and square root of 2, and put that over x and y for the legs and 7 for the hypotenuse. To solve, I need to take one of my ratios that has a variable and set it equal to the ratio that's complete, that I know both the top and the bottom number. So for example, I could write 1 over x equals the square root of 2 over 7. Then I can cross multiply and divide both sides by the square root of 2. So I get an answer of x equals 7 over the square root of 2. And you could show all that work again to figure out the length of y, but you really don't need to, right? Because since this is an isosceles triangle, these two side lengths must be the same, and therefore y must be 7 over the square root of 2 as well. Let's try another example. Except this time, one of the legs is a square root. It's the square root of 5. Let's see what that looks like when we solve. Since it's a 45, 45, 90 triangle, I'm going to use the ratio of 1, 1, square root of 2. One of the legs is x, the other one is the square root of 5, and the hypotenuse is y. To solve for x, we'll use the ratio that has x, and we'll use the complete ratio, 1 over the square root of 5. So if I use those two ratios, cross multiply, and solve, I find out that x equals the square root of 5, which again, we didn't really have to show that work, right? Since this is a 45, 45, 90 triangle, these two legs must be congruent to each other. But let's go ahead and solve for y as well. I'll use the ratio that has y, of course, and I'll set it equal to the complete ratio, 1 over the square root of 5. So this time when I cross multiply and solve, I have the square root of 2 times the square root of 5. Since these numbers are both square roots, you can just multiply the numbers underneath of the radicals together, and we get an answer of the square root of 10. Alright, let's try some 30, 60, 90 triangles. It's the same general idea, except we're going to use a different proportion. The proportion we'll use for 30, 60, 90 triangles is 1, square root of 3, and 2. 1 refers to the shorter leg, which is 10. 10 is the shorter leg because it's across from the 30-degree angle. Square root of 3 refers to the longer leg, which is x. The longer leg is the leg that is across from the 60-degree angle. And 2 refers to the hypotenuse, which is y. So if I want to solve for x, I'll pick the ratio that has x and the complete ratio, set them equal to each other, and cross multiply and solve. So my answer here is 10 root 3. I can't write that as the square root of 30 because one of the numbers has a square root and the other one doesn't. It's like they're not like terms, so you just have to leave it as 10 root 3. Now let's solve for y. I'll use the ratio that has y and the complete ratio. So 1/10 equals 2 over y, cross multiply, and I find that y equals 20. Our next example is also a 30, 60, 90 triangle, so again I'll be using the 1 square root of 3 and 2 ratio. Underneath of 1 I'll write x, because that's the length of the short leg. Underneath of the square root of 3 I'll write 8, because that's the length of the long leg. And underneath of 2 I'll write y, because that's the length of the hypotenuse. To solve for x, I'll use these first two ratios because it has x and because it's a complete ratio. Cross multiply. And I'm going to have to divide both sides by the square root of 3, so I get a rather ugly answer of 8 over the square root of 3. Now let's solve for y. I'll pick the last two ratios for this, the complete ratio and the ratio that has y. Cross multiply and solve. Divide both sides by the square root of 3, and I find out that y equals 16 over the square root of 3. For our last example, we have another 30, 60, 90 triangle, but this time one of my side lengths is labeled with a radical. Let's see what happens. I'll use the same ratio as the last two examples, 1, square root of 3, and 2. 1 is for the short leg, which is y, square root of 3 is for the long leg, which is x, and 2 is for the hypotenuse, which is 2 root 3. So to solve for x, I'll use the ratio that has x, which is the square root of 3 over x, and the complete ratio, which is 2 over 2 root 3. So when I cross multiply and solve this time, I get 2 times x, well that's just 2x, equals the square root of 3 times 2 times the square root of 3. I notice that there's a 2 on both sides of this equation. I could divide both sides by 2 to get it to go away. So then I just have x equals the square root of 3 times the square root of 3. Since these are both radicals, I can multiply the numbers under the radicals together and get 9. And we know that the square root of 9 is 3. Alright, let's solve for y. Y is part of this ratio, and I'll set it equal to the complete ratio, 2 over 2 root 3. Cross multiply. And again I see 2's on both sides of the equation, so I can divide both sides by 2, and I find out that y is the square root of 3. And that's all you need to know about special right triangles. In our next lesson, we're going to learn how to use sine, cosine, and tangent, which are trigonometric ratios, to calculate side lengths and angle measures in right triangles.